Hello everyone, Kotungwane, the Native God here. Welcome to the third lesson for Kinematics under Mechanotechnics N6. Right now, this is the third lesson. Right, I have two lessons that I've done prior to this one. Right, so if you haven't, if you haven't watched any of those, stop the video, go to the playlist, watch the first and second lesson, then come to the third. Right. In the first lesson, I cover what is this? Just the basics of kinematics, right? And then I cover the basics of kinematics thoroughly, right? So that moving forward, you understand the terms that we speak of, right? And then the second lesson, I specifically looked at the space diagram, right? How you go about drawing the space diagram, right? So if you are fine with the concept of kinematics, as well as how to draw the space diagram, right, and you want to know how to go about drawing the velocity diagram, then you are in the right place, right? Right, so in this video, I am going to show you how you would go about drawing a velocity diagram, right? As you know by now, before getting to the velocity diagram, you need to have drawn your space diagram, right? Now I did that in the second lesson, right? And this was our space diagram, right, for this problem, right? Now, if you notice, I haven't really prioritized what is this, or how can I put this? What I've prioritized in my lessons, right? So the first, second, and now the third is basically the understanding of the module kinematics, right? I believe if you do any and all problems regarding kinematics with understanding, then you will enjoy the subject, right? You will enjoy it very much. But how you enjoy the subject, or whether you enjoy the subject or not, is contingent on whether you understand the content or not, right? As you've seen, I haven't really prioritized doing a lot of problems, right? In the first three lessons, we haven't really done, say, a problem, right? I've just taken you through how we go about doing stuff. So how we go about drawing the space diagram, how we go about now drawing the velocity diagram, right? It is of utmost importance that you understand the basics, if you understand the principles surrounding kinematics, right? And it is of utmost importance that you know and understand how to draw a space diagram as well as a velocity diagram, right? Everything else that follows after you've understood that is very easy, right? So having to determine a velocity, right? Having to determine the acceleration, right? It becomes very easy once you are comfortable with drawing the space diagram as well as the velocity diagram, right? So again, on this video, we'll be looking at how we go about drawing the velocity diagram, right? And then in the video after, I'll then start looking at word problems, right? Or answering questions based on word problems, right? Right. Now, for the velocity diagram, right? At this point, I would think you now know that as far as velocity analysis, right? Which velocity we analyze if you're looking at a rotating body, or if you're looking at a body that is rotating as well as translating, and the velocity analysis we do for a translating link, right? So I'm not going to really explain much on that. I've already done so in the first and second lesson, right? Now, in drawing your velocity diagram, right, the first thing you look at is, right, the first thing you do is, the first thing you need to understand is, on your mechanism, right? Any and all fixed points. So any and all fixed points on your mechanism you take as 1 point, right? That 1 point is probably the most critical point in your velocity diagram. So that's the first point you draw on your velocity diagram, right? The first point you draw is a point that represents any and all fixed points, right? So if you look at this mechanism, right, we essentially have two fixed points, right? We've labeled them as O1 and O2, right? On the diagram itself, this is the point we take as O1, we're given this fixed point, and then the other fixed point, which on our space diagram we've labeled as O2, right? On the mechanism itself, it wasn't labeled, right? But we took note of the fact that a slider moves relative to the fixed point or this fixed frame, right? Hence, we named that frame as O2, right? So again, first point on the velocity diagram will be one that represents any and all fixed points on the space diagram, right? Right. So that's the first thing you take note of. Second thing you look at is the crank, right? So you look at how the crank is rotating, right? So this crank is rotating clockwise, right? So you take note of how the crank is rotating, right? The first velocity vector that you're going to draw on your velocity diagram will be 1 for the crank, right? So you look at how the crank is rotating, right? And knowing that the crank is rotating, you know you're going to analyze what? The tangential velocity. The tangential velocity of a rotating body must be such that it is perpendicular to the link itself, right? So as far as the direction of the velocity vector of the crank, right, it must be such that it corresponds with how the link is rotating. So if the link is rotating clockwise, so that is clockwise. So the link is going to rotate in this direction, right? So your velocity vector must be such that it corresponds to how this vector is going to be rotating, right? So because it's rotating clockwise, it means that tangential velocity, right? It means that tangential velocity will be in that direction, right? So once you've established the direction, right, the direction of your velocity vector for the crank, right, it gives you a sense of how your velocity diagram is going to be shaped, which then indicates to you as to where to place your fixed point, right? So because the direction, or because we've established that the direction of your tangential velocity of the crank will be in this direction, it means in placing your point here, we must place the point such that it is more to the left of your page, right? Because we're anticipating that the tangential velocity of the crank will be in this direction, right? So you place the fixed point more to the left of the page, right? Very important, right? So you place your fixed point. Once you've established that, you then place your fixed point, right? Place your fixed point. That point, right, this point represents any and all fixed points, right? So this essentially, right, so this essentially will represent O1 as well as O2, right? This will represent O1 as well as O2, right? So that's your fixed point, right? So that's number one, right? Then now, this I explained in the previous lesson as well. So second lesson, that in determining your, in drawing your velocity diagram, right? You have to determine of the 2 points on your link, which of those points is the link rotating about, right? Now, link OA, our crank is rotating about O1, right? So meaning that the tangential velocity for crank OA will be the velocity of A relative to O1, right? Now also I want to mention that as far as velocity, right? If the frame of reference is a fixed point, right? If the frame of reference is a fixed point, so just like this velocity here, right? The frame of reference O1 is a fixed point, right? If the frame of reference is a fixed point, then you can take that velocity as an absolute velocity. Taking this as an absolute velocity, that means this is the same as just saying this is equal to VA, right? So again, if the frame of reference, right, of your relative velocity is a fixed point, then the velocity, right, for that link is essentially an absolute velocity. So it can be expressed as just VA, A being the object, right? So essentially for crank OA, we are looking for VA or VAO, right? Now, we've established that A is the object and O1 is the frame of reference. Now, we already have a point that represents O1, right? And having to draw the tangential velocity, right? So VA, having to draw VA, we know VA is going to pass through this point, right? And not only that, it will pass through this point. And since we've also established the direction of the vector itself, right, we know that we won't have to draw a line going upward as well as downward, right? We'll just draw a line going in that direction since we've already established that direction of the tangential velocity of crank OA, right? So now, using this scale, right, I forgot something here. So before having to use the scale, you first have to calculate the velocity of the crank, right? Now, as far as the velocity of the crank, you look at what you've been given. They said the crank OA rotates clockwise at 45 radians per second, right? So radians per second is angular velocity. So they've given us the angular velocity of the crank OA. So we use the angular velocity of crank OA to get the velocity of the crank, right? Or the tangential velocity of the crank, right? Now, from angular motion, you should be familiar with this. V from angular motion, we know is equal to omega times R, right? Now, this we've already been given. This is what we're looking for, right? So essentially, okay, let us be accurate here. So we are looking for VA. So VA will be the angular velocity of OA, right, times R, right? Now, this we've been given, and R, the radius of the link, we know is equal to the length of the link, right? So R here can essentially be replaced with just OA being the length of the link OA, right? So this is what you're looking for. We have the angular velocity, it's 45 radians per second, times OA, which is 40 millimeters. That in meters will be 0.04, right? So then you calculate this, and then in calculating this, we get 1.8 meters per second, right? So VA is equal to 1.8 meters per second, right? Now we need to represent the 1.8 meters per second onto the velocity diagram, right? Now, as far as the scale, if we say, remember in the previous lesson I said your scale must be such that it is specific to the diagram you want to draw, right? So at the moment, we are going to draw the velocity diagram, right? And the purpose of a velocity diagram is so that we are able to determine the velocities of the links using the velocity diagram, right? So essentially, your scale for the velocity diagram will be convenient if you make it such that it is easier to calculate or to determine the velocity, right? So the way we do that is you look at your velocity of the crank. It's 1.8 meters per second, right? If we were to say our scale is going to be 1 centimeter is equal to 1.8 meters per second, right? That scale would be too small. Why? Because in drawing your velocity diagram, right, it's more than likely that the longest velocity vector on the velocity diagram, right, will be the one of the crank, right? So it's more than likely that the longest velocity vector on the velocity diagram will be the crank, right? So if the crank is the longest and you make the crank to be essentially 1 centimeter, right, it means your velocity diagram will be very small, right? So bearing that in mind, we then come up with a scale that will be reasonable, right? So what I did was I took the velocity, right? Its representation on the velocity diagram, I want to multiply it by 5, right? So essentially we say 1.8, right, times 5, and that's 9, right? So meaning multiplying this by 5, getting 9 centimeters will be a representation of the velocity vector of 1.8 meters per second, right? That to me seems like a reasonable scale, right? And then in writing it down, right, remember we are saying want to multiply the velocity by 5, right? So in wanting to multiply the velocity by 5, it means essentially this will be 5 centimeters is to, 1 meter per second, right? We want to multiply the velocity by 5, hence the scale would be 5 centimeters is to 1 meter per second. And then in solving for x, which will be the distance or the measurement that represents the vector 1.8, right? If you look here, if you cross multiply, essentially you are multiplying this by 5, which is exactly what you're looking for, right? Now, once that has been determined, right, the next thing you want to do is you want to make the scale such that it is convenient to calculate what the velocity once you are done drawing the velocity diagram, right? The only way to do that is you then divide both sides. So essentially you are trying to make the coefficient here of the centimeter. You want to make this 1 centimeter, right? So you divide both sides by 5, right? And then what do we get? We get 1 centimeter is to 0.2 meters per second, right? Now the scale is convenient for having to determine the velocity, right? Meaning if say you want the velocity of the link and that link is 9 centimeters long, right? You see 9 centimeters here is to x. To get x now, you would then simply cross multiply, right? So once you're done drawing the velocity diagram, right, to determine the velocity of each link, right, you're simply going to take its measurement and multiply it by whatever you have on this side. That's what I mean by make your scale convenient to determine velocity, right? That is where this scale comes from, right? Right. So we've determined that the velocity of the crank, the tangential velocity of the crank is 1.8, right? And 1.8 meters per second is going to be 9 centimeters, right, on our velocity diagram, right? Now, again, I do not have set squares, right, the instrument that you will be using, but I am going to take you through how you would use your instruments, right? Now, all you do, remember this has already been drawn, right? Our space diagram has already been drawn. Another thing, one of the reasons why um, your space diagram mustn't be too big, right, is so that you are able to draw the velocity diagram just below your space diagram, right? And the reason why you need to draw your space diagram just below your space diagram, the reason why you need to draw your velocity diagram just below the space diagram, right, is because in drawing the velocity diagram, you have to make use of your set squares, right? Remember, we've determined that the tangential velocities of the rotating links, right, must be such that it is perpendicular to the link, right? So what you will do is you already have this point which represents n and all fixed points. Now you want the tangential velocity, which you know will be 9 centimeters in this direction, right? So in this direction, which you know will be in that direction, right? So what you do is you place your 45 degree, right? You place your 45 degrees set square parallel to this line, right? Place your 45 degree set square such that it is parallel to this line, right? Place it parallel to this line, and then you take your 60-degree one and you place that one such that it is perpendicular to the 45 degree set square, right? So again, you want to draw a line that is perpendicular to this link. That line will represent what? Will represent the tangential velocity of the link OA, right? So what you do is you are drawing the velocity diagram below the space diagram, right? So to get that line that will be perpendicular to the link that you will draw here passing through a point 01, 02, you place your 45 degree set square parallel to link OA, right? And then you take your 60 degree, 60 degree set square, right? So the 60 degree one is the longer one, right? You place that one perpendicular to the 45, right? So you place it perpendicular to the 45, right? So that one you will place such that it is perpendicular, right? So the 60 degree one you will place such that it is perpendicular to the 45 degree one, right? Now all you do is the one that is perpendicular to the link, right? That one you are going to shift along the 45 degree one, right? By that I mean you're going to shift it such that it then aligns with this point here, right? So you're going to shift this one. So the one that is perpendicular to the link, you shift it, right, such that it then aligns with this point, our fixed point. When it aligns with the fixed point, so essentially this is 60, 150. Right? So what I mean is you can take this ruler feature, right, as your 60 degree one. So take the ruler feature as the set square that is perpendicular to the link. So I mean you've placed it perpendicular to the 45 degree set square. Now you shift it, right? You shift it in such a way that it then aligns with your fixed point, right? Where it aligns with your fixed point, you then draw a line, right? You then draw a line going in this direction. This line must be faint, so you draw a faint line, right, going in that direction, right? Remember, we had already determined that our tangential velocity for the crank will be in this direction, right? So you draw a line going in the same direction, so going in this direction, right? That line must be such that it is a faint line. This must be a faint line, right? Once you've done that, You then, because remember we had already determined that the velocity VA, right, will be equal to what? 9 centimeters on the velocity diagram. So you then now use your ruler, you measure 9 centimeters, right? You now measure 9 centimeters. You've already drawn this line, remember? You now measure 9 centimeters, right? Right, you measure 9 centimeters, right? Once you've measured 9 centimeters, you then draw a line that is bold. So you bolden the line to 9 centimeters, right? So you bolden the line to 9 centimeters, right? And then what you do now is you remove your faint line, right? And now this line represents the 1,8 meters per second, which is what? VA, right? Which is VA, right? Now remember, the velocity of this crank is what? Is VAO, right? A being the object, O being the frame of reference. We already have a side of this velocity vector that represents O1, means this side will be A. So this side will be, so you'll have A on this side, right? Right? So you'll have A on this side, right? Now, as far as direction, right? Now for the crank, it's pretty obvious. We had already established the direction anyway, right? And that direction, we said is going in that direction, right? Now for other velocity vectors, right? There's a good chance that you won't have determined you won't have predetermined the direction, right? So how you determine the direction is the direction of each of the velocity vectors must be such that they are pointing towards the object, or you can say pointing away from the frame of reference, right? For instance here, right, for this velocity vector VAO, A is the object, O is the frame of reference. Hence, if you look at the direction, it is pointing towards the object, right, or pointing away from the frame of reference, right? So that is the easiest way of determining direction for the other velocity vectors, right? Right. So now we have VA essentially, or VAO, right? Next, we are going to look at the tangential velocity of link AB, right? Right, now means we are at this point, means that we're looking for VB. B is the object, right? B is the object and A is the frame of reference, right? Now on our velocity diagram, we already have point A, right? Since we already have point A, right, it means however we draw the velocity for this link, it must be such that it passes through this point, right? It must be such that it passes through this point, right? Right, now let's say this is 180 minus 17, say minus 90, right? Now, so now you're going to do the same thing we did when having to draw the velocity vector for the crank. Remember what we did was you place your 45 set square parallel to the link, and you place your 60-degree set square perpendicular to the 45, right? And then you shift it such that you align it to this point, right? So now we're going to do something similar. But now, since we're looking at link AB, you are now going to place your set square parallel to link AB, right? You're going to place it parallel to link AB, and then take your 60-degree one and place it perpendicular to, right? You place it perpendicular to the 45, right? And then all you do now is you shift this one along the 45-degree one, right? So you shift the 60-degree one that is perpendicular to the 45, right? You shift it along the 45 one, right? You shift it along the 45-degree one such that it aligns with this point, right? Remember, we established that VPA, or the line that represents VPA, is going to pass through A, seeing that we already have point A, right? So then once you have that, or once you've established that, you then draw a line, right? Now remember that you at this point, you don't know if this is going to go in that direction or this direction, right? So you can either draw it going in both directions, so meaning draw a line, right? So meaning draw a line that's going essentially in both directions, right? Seeing that you don't necessarily know in which direction it's going to go, right? Or you can look at the fact that, remember here you have VPA, right? You have VPA, right, which is the tangential velocity of this link, and then you also have the velocity of the slider, right? Remember, you also have the velocity of the slider, right? So at point P, you essentially have two velocities. You have VPA, which is the tangential velocity of link AB, and then you also have the velocity of the slider, right? Now, both of those velocities, are going to pass through B, right? Remember, you have VPA, and then the velocity of the slider. You look at how the slider is moving. The slider is translating, right? The slider is translating, and it is moving relative to what? The frame which we called as O2, right? So you have a slider here, and it is moving relative to the frame. So essentially at point B, you have the tangential velocity of AB as well as the velocity of B relative to O2. And remember what I said about if a velocity, or if the frame of reference of a velocity is a fixed link, right? You can essentially take that velocity as an absolute velocity, right? Meaning that at point B, you have two velocities, the tangential velocity of AB as well as the absolute velocity, right, of B, which is the velocity of the slider, right? So you can bear that in mind, right, that you have two velocities here, and both velocities have to pass through B, right? So now you have a line, right? So before drawing this line, you know that the line that represents the velocity of B, so the absolute velocity of B, right, or velocity of B relative to O2, that is the velocity of the slider, right? Remember, it's moving horizontally, right? You can establish that the direction of this line must be such that when you draw the velocity, the absolute velocity of B, right, they will be able to meet, right? Now we know that the velocity of B is horizontal. It'll either go in this direction or that direction, right? Now for the line to meet with this line that represents B, it means it has to go in this direction, and that tells us clearly that the direction of this line must go in that direction, so that it's going to be able to meet with the velocity of the slider, right? So those are the two approaches you can take, right? You can either draw a line going in both directions, right, and then just continue drawing your velocity diagram. When you get to having to draw the velocity, the absolute velocity of B, so VB with respect to O2, right? You have to draw a line that is horizontal that passes through the fixed point. That line will either go in that direction or this direction, right? But because we know that we have a line that represents B on this side, it means it's going to go in this direction. So when you draw the line, right, let's make this one blue or let's make it white. So now when you draw the line, right, this is where this line and B meet, meaning B is going to be this point, right? Remember that this one was faint, right? So the faint lines, make sure you make them very faint, right? Make sure you make them faint so that they're easy to erase, right? And then once you've determined that this here will be point B, right, you now can make this line bold. So you take this ruler, take your ruler and make that line bold, right? And then you remove your faint line, right? Right. Now, remember, as far as direction, the direction of a vector must be always such it must be always such that it points towards the object or points away from the frame of reference, right? Now remember, we had already determined that VP here, B is the object and A is the frame of reference, right? So meaning for this vector, the direction will be in that direction, pointing towards the object. So for link AB, the object is B and A is the frame of reference, right? And then regarding the absolute velocity of B, right? VB being the absolute velocity means that B is the object. So meaning the velocity of the slider, so VP or VBO will be in that direction, pointing towards the object or pointing away from the frame of reference. Right? As far as directions go, that's how you determine direction, or that's the easiest way of determining direction. Right? Once you have this, right, it is convenient to label your velocity diagram, right? So as we determine that's VB, right? And then we have VA, right? We determine that this here is VA, right? So we determine that this is VA, right? And then as far as AB, you have VBA, right? This you've already determined, so that's VBA, right? And then you of course measure each vector, right? Remember, we had already determined that VA is what? 9 centimeters, right? We had already determined that VA is 9 centimeters, right? So that's 9 centimeters, right? So when you measure VPA, right? When you measure VPA, I got what did I get? I got 4,9, right? So I got 4,9. So I got 4,9 centimeters, right? You do not necessarily have to get exactly the same measurements as me, right? You could get, say, 4,8, maybe 4,7, as long as it's close, it's not a train smash, right? And then I got 9.1 centimeters for VB, right? So the measurements you would write on the outside of each vector, right? And then the labels as to which velocity vector we are looking at. So this here, right? Those you put on the inside, right? Right. I hope this was clear to all of you. Right. I believe I tried my best to explain as to how you would draw a velocity diagram. Right. So if you're somewhat still struggling, just go over this video, right, until you get it right, so that when you move on to other videos, right, it becomes less and less difficult. Right. Now, we have a point here, right? On the statement, they said the center of gravity. So we have the center of gravity, G, right? You have point G, right? Now, they sometimes like asking you guys to calculate the absolute velocity of G, right? Which would be Vg. So meaning that you would need to get point Vg right here as well, right? On the space diagram, point AG is within link AB, right? So even on our velocity diagram, point G will be on the vector AB, right? So it should be somewhere here, right? So point G from A will be somewhere there, right? So the way we go about getting that point, right? So the way we go about getting point G, right, is by simply using this here, right? So we say we are looking for AG on the velocity diagram, right? Now, if you notice, as far as labels on the space diagram, I used capital letters, right, to distinguish between the space and velocity diagram, right? I then use small letters on the velocity diagram, right? So we are looking for AG. So I say this is how you calculate the measurement of AG. So you say AG, right? So AG on the velocity diagram divided by AG on the space diagram is equal to, now the point G is on link AB, so we then say is equal to AB on the vector diagram divided by AB on the space diagram, right? Now if you look at this, this is what we are missing. We have this, and we have this. So solving for AG for the vector diagram, right? This will be AG is equal to, so this will be AB divided by AB times AG, right? So this will be, now AB on the velocity diagram is 4,9, right? So I use 4,9. So this will be 4,9 divided by AB on the space diagram. AB on the space diagram is 120 millimeters, right? Which is equal to what? Which is equal to, what is this? In centimeters, that will be 12, right? So divided by 12, right? Because remember, this is in terms of centimeters, times the AG of the space, right? AG of the space diagram is 40 millimeters, right? 40 millimeters in centimeters is 4, right? And then you get 1,6 centimeters, right? You get 1,6 centimeters. Now, once you have that, all you do now is take your ruler, right, and you measure 1,6. You measure 1,6 on your rulers, right? Measure 1,6 on your rulers, right? Right, 1,6 is at that point, right? So you have a point that represents point G on the velocity diagram, right? Now all you do is, once you have that point, you simply take your ruler and draw a line from the fixed point to where point G is, right? So this will now have to remove. So this is point G, right? Now this here is from A to G is 1,6 centimeters, right? Meaning what's left over is what? From G to B, we have 3,3 centimeters, right? And then as far as the direction of this vector, right? See where this line is coming from. The line is coming from a fixed point, meaning that this line represents the absolute velocity of what? Of G, right? Remember that if your frame of reference is a fixed point, then the velocity will then become an absolute velocity, right? So essentially, this here is what is this? VG, right? So G being the object means as far as direction, this is going in that direction, right? Then you measure the line OG, right? You measure the line that represents VG, and I got 8,7 centimeters. Right, I got 8,7 centimeters. Right, and that is how you would draw a velocity diagram. Right, that is how you would draw a velocity diagram. Right. Right. Now, in the next lesson, I will take you through how you would then determine the velocity, right? Once you've drawn your velocity diagram. But I do believe it's actually pretty straightforward now, right? It's pretty straightforward, right? At this point, you have your velocity vectors, right? So using your scale, essentially, you then calculate your velocities. So if you're asked to calculate the velocity of B, so let's look here. For instance, if you look here, they said determine the velocities of the slider B, right? You know the velocity of the slider is VB, right? I've already taken you through how we determine that, right? And point G. Point G, I've already explained. So essentially, they're looking for VB and VG, right? Which I've already taken you through how we go about getting point G, right? And then if they ask you to calculate the velocity, they said determine the velocities of slider B and point G. The velocity of point G will be the absolute velocity, right, of point G, which you will get by drawing a line from the fixed point to where you have point G, right? So you take, for VP, take the measurement 9,1 centimeters, use your scale, right? So essentially it's going to be 9,1 times this, that will give you VB, and VG, you take this measurement, you multiply it by 0,2 using your scale to get VG, right? That is why I put so much emphasis on, in the first 3 lessons, that is why I put so much emphasis on the approach, on the concept, right? So that you understand what you are doing. By the time you get to having to determine the velocity, right, it becomes a walk in the park, basically. Right? Right. In the next lesson, I will be going through how you determine velocity and how you determine centripetal acceleration. Right? Right. Hope you enjoyed the video. If you did, please like and subscribe. Also hit the notification bell so that you do not miss any of the content which might be helpful to you. Right? Hated God, signing out.